If you have ever taken a basic course in physics, you may have seen something like this. What we have here is a representation of the gravitational attraction of a central mass in one slice of 3D space. Of course, all the arrows point towards the center, and the color scheme indicates that the arrows grow stronger towards the center. These arrows tell you how an object located in the plane will move, or more precisely, how it will be accelerated. For example, an object in a stable orbit about the center will continuously be accelerated towards the center, always in the direction of the arrows, just so that its orbit forms a circle or something similar. It is not actually moving in the direction of the arrows, quite the contrary, but it is always accelerated in their direction. Mathematically, we can think of two numbers being associated with each point in space, since the arrows are defined by their length in the x and in the y direction. So in 3D space we would have three numbers at each point, the components of the arrow along the x, y and z directions. This is how Newton formulated his mechanics. At each point in space, you have a force vector, and as an object moves through space, it is accelerated dynamically by these force vectors. That is what his second law, F = ma, states. The acceleration at each point is proportional to the force, with the constant of proportionality being the mass. In this video, we will always assume that we are using the same test object of constant mass and treat force and acceleration interchangeably. While spectacularly successful, the mathematics of Newton's theory were often cumbersome, and many problems that were a little more complex could not be solved effectively. In the 150 years following Newton's foundational work, his theory was reformulated multiple times. Nothing fundamentally new was added. The same physical model was just put in different mathematical terms, which proved much more effective at handling those complex problems. The principal difference to the original formulation was that the force concept was discarded in favor of a description based on energy. Instead of the three numbers of a force vector, you assign each point in space only a single number, which is the energy an object located there will have just by virtue of its position, independent of how much kinetic or mass energy it has beyond that. We commonly call this form of energy the potential energy. In 3 dimensions, that can be visualized by something like a density distribution. You can picture a cloud, which in some areas is more dense, where the energy is higher, and in others it is more rarefied, where the energy is lower. But we don't lose much by thinking in 2 dimensions. The basic concepts work just the same way here, and it can be visualized much more elegantly using a surface. To each point xy we assign an energy set, which we graph as a surface which has height z over or below the point xy in the original flat plane. Keep in mind though that the height does not necessarily represent a physical position. For that only the x and y coordinates matter. But that is nonetheless a good way to gain some intuition for the formalism. Where the idea of the arrows was that they nudged an object along, the intuition for the energy surface is that the object rolls along the surface, tending to accelerate downwards in the direction of decreasing energy, just like an object held in your hand has more potential energy in the gravitational field of the Earth than one lying at your feet, and if you let go, the object you held will accelerate downwards, lowering its potential energy by converting it to kinetic energy. Incidentally, the energy-based formulation was not only much more powerful in practical terms for solving problems, it also proved much more well-suited for the transition from classical to quantum mechanics. And so if you look at the Schrödinger equation, which replaced Newton's F = ma in the 1920s, you won't see any forces, it is completely based on energy. The most fascinating thing about this to me, though, is that you can seemingly drop 2/3 of the information you have without really losing any in going from the force view with 3 numbers to each point to the energy view with only 1 number at each point. You can even recover the original force formulation. Now let's have a look at a simple pet system to build some more intuition. A ball rolling across the surface of hills and valleys. This is perfectly suited to the energy formulation. We are automatically in 2D since the movement of the ball is constrained to the surface, and the spatial height of the surface automatically encodes the energy field. Now, of course, we can also formulate that in terms of force vectors. Basically, at each point we will have an arrow which points down along the surface, whatever that exactly means, and the more so, the steeper the descent. For an initial naive construction, we can look at it dynamically. Of course, as we have seen, an object moving through a force field doesn't necessarily move in the direction of the arrows. That is only the direction in which it is accelerated. But when we place an object somewhere in the field at rest, the direction in which it will start to move instantaneously is the direction of the force, and the magnitude of the force is proportional to how fast it is accelerated. You can think of it as placing the object, waiting a very short time interval, say 1 second, and measuring the direction in which the object has moved by then, and the speed it has acquired. The force vector will point in the direction in which the object has moved, and the magnitude of the force vector is proportional to the acceleration which the object has experienced, which is the velocity acquired per unit time. So if we wait 1 second, that is the final velocity divided by 1 second. To be rigorous, we then let the time interval, the 1 second, go to 0 and settle on the direction and magnitude towards which we converge in that limit. This way we can build up our force field. And once we have that, we can actually drop the curvature of the surface, just like we can use a plane map to get around on our curved Earth. X and Y, or longitude and latitude, are enough to fully specify where you are, and the arrows tell you how you will move along in those coordinates. Similarly, we can keep the energy formalism and still get rid of the curvature, which is, after all, just a way of assigning each point in the flat plane a number in the continuum. We can use a continuous color scheme instead. Or even just explicit numbers. Often it's most intuitive to have both height and color at the same time though. But ultimately it's always just a way to represent a number assigned to each point in the xy plane. To get a better sense of how the arrows and the surface encode how an object moves through space, let's look at the most simple system that can illustrate this. A homogeneous force field where all the arrows are of equal length and point in the same direction, in our case downwards. We let an object enter this force field horizontally, displaying its horizontal and vertical velocity each by an arrow at the side. The horizontal velocity will remain constant, since the force vectors point downwards, and so only affect the vertical component. In each instant of time, the arrows nudge the velocity a little bit in their direction, in proportion to their length, and so here the vertical velocity just grows linearly in time. As Galileo discovered in the early 17th century, the object thus accelerated describes a parabola. Of course, that is what we experience all the time, with the, on human scales, homogeneous field of gravity on the surface of the Earth. When you throw a ball, its horizontal velocity remains unchanged, neglecting friction, but the vertical velocity grows in proportion with time, and so the ball's trajectory arcs downward. And so just like the gravitational potential energy of an object on Earth is proportional to its height above the surface, the energy field describing this system is one where the energy increases linearly when you go against the direction of the arrows. You can think of it as the energy you require to overcome the arrows which try to push you back down. On the other hand, the arrows don't care how you move horizontally, since they have zero component along that direction. So you don't have to work against them, and so the energy doesn't change as you move right or left, just like you don't have to expend any energy except to overcome friction when you roll a ball over a flat plane. Now, in the energy formulation, our object is accelerated towards decreasing energy, which of course produces the same trajectory as in the arrow formulation. Again, we can use height, color, or just plain numbers to visualize the energy field. So now that we have looked at a few simple systems and built some intuition, we can start to get more serious about switching between the two formulations. You don't want to have to place a ball at an infinite number of points to determine the force there, so let's start with how we can get from energy to force more systematically. Again, it is often useful to start in very simple systems, so let's begin with a one-dimensional one. Here we have this oscillating one-dimensional energy surface, and we want to construct the corresponding force vectors. As we said, force vectors point in the direction of decreasing energy and are proportional to the steepness. That is very simple in one dimension, since there are only two directions to choose from, and it's pretty clear which of them, if any, is downwards. The magnitude, i.e. the steepness of descent, tells you by how much you go up or go down as you go a little bit to the side. In other words, it is equal to rise over run. Now that of course depends on how much you go to the side. Here, we are not interested in the average steepness across some interval, but the steepness at some point. And so we use a limiting procedure, where we let the distance we step to the side go to 0, and see to which steepness we converge. As you've probably recognized, what we are doing here is simply taking a derivative. Now, the derivative already includes not only the magnitude of the force, but also its direction. It is always positive, where the energy is increasing in the positive x direction, and negative, where it is decreasing. We are interested in the reverse. The arrows are supposed to point in the direction of decrease, not increase, and so we define force as minus the derivative. It's pretty straightforward to go from there to higher dimensions. On a two-dimensional surface, we can think of the x and the y direction separately. The ball will be accelerated along the x direction in the direction and proportion of the descent along the x direction. So for the x component of the force, we can take the derivative of the energy by the x coordinate while keeping the y coordinate fixed. This is called a partial derivative. And again, take its minus. The ball will simultaneously be accelerated along the y direction, in the direction and proportion of the descent along that direction. So we also take the partial derivative for the y direction to get the y component of the force. We then get a vector in the combination of these two force components, which is minus the derivative of the energy function E, first by the x and then by the y coordinate. This construction, without the minus, is also called the gradient of the function f, represented by a little triangle on its head, and can be generalized to 3 dimensions in the obvious way. So the gradient is always an arrow pointing in the direction of greatest increase. And our basic result is force is equal to minus the gradient of the energy. Let's have a look at a concrete example. Here we have a simple hill as our energy surface, constructed as a Gaussian function, which is an exponential function of the squares of our coordinates. We can take the partial derivative by x and by y respectively, treating the other coordinate like a constant in each case to get the gradient. Putting a -1 in front of it to get the force, we can simplify the expression to a magnitude, which is another Gaussian, times the vector xy of the position itself. So the force always points away from the center towards the current position, except at the center itself where it is 0. Near the center, the exponential part will be roughly constant at 1, meaning the xy part corresponding to the distance from the center determine the strength of the derivative, so that the force initially grows with distance from the center, and then the exponential term, which goes to 0 as the distance increases, starts to dominate, and the force diminishes. That all fits perfectly with the intuitive picture of a ball rolling down the hill. First it gets steeper, then it flattens out again. Now let's see how we can conversely go from the force formulation to the energy formulation. We start by having a closer look at the homogeneous force field seen earlier. First of all, for our dynamics, only steepness, i.e. differences in energy matter. we don't care about the absolute values of the energy, and so we can assign some convenient point where the energy is 0. Let's call that point A and place it in the center of our plane. Then, to find the energy at some other point B, we need to figure out the energy difference between A and B. How much energy do we need to give an object to move it from A to B? Or, if the energy at B is negative, how much kinetic energy does the object gain in being accelerated by the field when it goes from A to B? Let's look at a special case first. When we go only straight against the force field, we bear its full brunt, and so the energy it takes to get from A to B is directly proportional to the intensity of the force. Of course, it is also proportional to how far we go. So the energy of a point B lying along the field, as seen from A, is just the intensity of the field times the distance between A and B. It doesn't really matter how we go from A to B, so it is only about distance, not about time. After all, the energy field only depends on position, so it only cares about where we start and where we end up. There are cases where things are more complicated though, as we'll discuss at the end of the video. Now, on the other hand, if we go perpendicularly to the field from A, we do not have to expend any energy, and neither do we gain any. Of course, we have to resist the field to stay on that perpendicular line, but that is a static situation where nothing changes, and so the energy remains constant. The perpendicular movement itself can be accomplished by pushing the object arbitrarily softly, like a ball rolling along a flat plane. So the energy on the axis through A, which is perpendicular to the field, is everywhere 0, the same as at A itself. Now, we can combine these two ideas to get the energy at any point. First we go a little from A along the field, and then we go from there perpendicularly to the field. Obviously we can reach every point that way, and so we can build up our full energy surface. Okay, now let's move on to a more general messy case, our hilly surface from the beginning. The immediate problem we encounter is that we cannot just go along some direction where the force is constant and multiply force by distance, because the force varies everywhere, there is no direction along which it is constant. If, however, we zoom in and only go a tiny distance, the force is nearly constant along that short path. And so the idea now is that we can once again choose some point A of 0 energy, and then if we want to find the energy at some other point B, we draw a path from A to B and chop it up in short segments. Then we multiply the length of each segment with the force along that segment, as in the homogeneous field, and add up all these contributions. Of course, the value we will get depends somewhat on where we take the force arrow. In the beginning of the short path segment versus the middle, for example. But we can get rid of that ambiguity by doing another limiting procedure, in choosing ever finer segments, and so letting the segment length go to 0. Formally, we are taking what is called a path integral. And so we can do all that for every point in the plane, and so build up our full surface once again. Of course, this seems at first glance like a very complicated procedure. We don't want to have to do all that for every single point in the plane. So let's go through a specific example and see how we can actually calculate the energy from the force systematically for every point. We will take by far the most important real-world example, a central mass point and its field of gravitational attraction. It's not just about gravity though. Electric charges produce electric fields that take exactly the same fundamental form, for example. So we have our central object, towards which a test object is continually accelerated, and towards which consequently the force vectors all point. The magnitude of the force vectors is given by Newton's formula for gravity, based on the distance r from the center, as well as the masses m1 and m2 of the central object and our test object, as well as the gravitational constant g. In many problems in physics, we can simplify our calculations based on symmetries. Here we have an angular symmetry about the center. We can rotate the whole plane around it, and nothing changes, so the energy field must exhibit the same property, and be constant on each circle centered on the central mass. We can also see that more directly. If we draw such circles, we see that all the force vectors stand perpendicularly on them, and so it doesn't take any energy to move along them. So all we need to do is figure out the energy on one line going off from the center to infinity. Then we can sort of rotate it around the plane to get the full energy surface. Now we choose our point A of 0 energy, and in this case put it not at the center but all the way at infinity. This is more convenient because the center point itself is kind of messy here. The problem essentially is that we pretend that our central mass is only a single point, not an extended sphere, which works fine as long as we are outside of the actual sphere we are modeling, but it breaks down when we get too close. You can see that in Newton's formula for the gravitational force. At the center, the distance r to the center is of course 0, and so we have a division by 0 in the formula, and our model breaks down. So let's place A very far away instead. Now, we apply the procedure we have just built up. We choose some point B along the straight line from the center to A and chop the path between them up in small segments. Let's start with segments of length 1. The force arrows point from A to B everywhere, and so instead of having to put energy into the object to move it from A to B, we get some out, and the energy at B will be negative. We calculate it by choosing the force magnitude for each segment to be that at the end of the segment. As we have seen, that choice in the end doesn't really matter when we let the segment length go to 0. To get some actual numbers out, we arbitrarily set the constant factor in the force formula equal to 20. Then we multiply each of these forces by the segment lengths, which we have conveniently chosen to be 1. Of course, one complication here is that we have an infinite number of segments, since A is infinitely far away, but that isn't a real problem, since the force decays so fast with distance that the infinite sum still results in a finite value. If you're having trouble with that idea, think of adding 1/2, plus 1/4, plus 1/8, and so on. You can picture that as rectangles of those areas lining up, and you will find that you can fit all this infinite number of rectangles into a single area 1 square. After all, each additional rectangle fills exactly half the remaining space, so you will never step outside it. In our case, with B located at distance 5 from the origin, the sum starts at index 5 and goes over all integers up to infinity, and each summand, one for each segment, is minus 20 over the current index, which is the current distance from the origin at the near end of the segment, squared. There's no need to evaluate this explicitly though, since of course this is only a crude approximation. To get the correct energy value at B, we need to let the step distance, which is currently 1, go to 0, which means we need to replace the sum with an integral. The infinitesimal dr replaces our distance factor. The minus 20 over r squared remains, and we again go from r equal 5 to r equal infinity. Evaluating this integral, we simply get minus 20 over the distance of B to the center. And that is the general formula for the energy. So if we let B move from A to the origin, we get a curve under the plane corresponding to that energy function. Rotating that around the origin, we get the whole energy surface, and so we are done. The 20 was simply the constant factor g times m1 times m2, so the general result we have just derived is an alternative formulation for Newton's law of gravity. In the gravitational field of a mass m1, a second object of mass m2 is equal to minus g times m1 times m2 divided by the distance d. This is all very pretty and neat. However, not all force fields have such a simple correspondence to energy fields as those we have discussed. There are two basic problems. First, you can construct vector fields that, like the ones we have seen, are static, constant in time, but where no consistent energy field can be constructed, because how much energy it takes to go from A to B depends on which path you choose. A simple example is this rotational force field. You can assign some point A the energy 0, but then, if you start going around the field in a circle from there, you can go against the field constantly and still end up back at A, which implies that the energy at A is higher than the energy at A. Or if you go around the circle in the other direction, pushed along by the field constantly, you find that the energy at A is lower than at A. Clearly our construction fails here. There is no consistent way of assigning energy to any point. Also, energy is not conserved here, since the object B can gain kinetic energy while moving on a circle, and so the kinetic energy can just grow and grow, even though everything else stays the same, so the total energy changes, because no loss of potential energy compensates for this gain in kinetic energy. For this reason, we call such fields non-conservative force fields, in contrast with the conservative force fields we have seen previously, where the change in energy of an object depends only on the start and end points and not on the choice of the path in between, and where energy is conserved. Now this example is more about mathematics than it is about physics. In physics you won't find a static field that gives an object unlimited kinetic energy without compensation. But there are examples in physics that are similar. For example, if you include friction, an object sliding along a circle will return to its original point with lowered energy. But in that case the field is not even static, since it depends on varying properties of the moving object, which brings us to the second problem. Force fields can depend on the velocity of the moving object, and that makes things much more complicated. The object sliding on a circle will experience greater friction when it's faster, so the force field is not constant, meaning it not only depends on the position, in contrast to those we have seen previously in this video. Another example is the force due to a magnetic field, which, per the Lorentz force, also depends on the velocity of the moving object affected by it. Take this magnetic dipole, for example, which you can think of as a little bar magnet, or perhaps simply an electron, which produces the same basic field. You can get a sense of its three-dimensional form from these moving slices. Note that this is the magnetic field and not the force field. Now, even though the magnetic field is constant, the force it exerts on a charged particle will depend on that particle's velocity. We can plot the velocity of a charged particle as a yellow vector, and the force in a slice of space which the particle would experience if it were located there while moving with the given velocity. As the velocity changes, the force field changes with it. This makes the construction we had been using up to this point impossible to work with, because that was based on static fields, where only the position is relevant for determining the force. So neither of these forces can be represented by a scalar field of potential energy in the simple way we have used here. Still, magnetism can be formulated in terms of energy, but in quite a different way from what we have seen so far, and so that is a story for another day.